We'll now move on to our next speaker, which is who's from ETH, Professor Dirk Moore. The stage is all yours. Go ahead.
Can you guys see the screen or?
Not yet. Yeah, I think it should be. Yeah.
See it now? Do you see the it in slideshow mode or just?
No, it's just the slide view.
Okay. Can you still see it or?
No. Yeah, you're on now. Yes, go ahead.
All right. Okay. Well, I'm glad that the screen is working. And first of all, let me start by saying that it is indeed a great pleasure for me to be a part of this symposium organized in honor of Professor K.R.Y. Simha. And I want to thank Professor Narasimhan for inviting me to this symposium. And I want to congratulate Professor Simha for at the occasion of his retirement. And I hope that his retirement is only on paper and he continues to mentor students. He's a great mentor and contribute to the field of experimental mechanics. So and I have known Professor Simha for a long time. Actually, if I remember correctly, I met him first in 1978. And Simha, you can correct me, it was 78, I think, not 79, when you came as a graduate student to University of Maryland. And I was already there as a graduate student, and we worked in the same group with professors. Some of them, actually most of them have now retired, and then some of them are no more. Professor George Irwin was the leader of that group. Professor Jim Daly, very well-known experimental mechanics person, and several other professors in that group. And Simha and myself, we had a lot of common interests. I think in the lab, we did experiments that were for our doctoral degree that were somewhat similar in nature. What I remember of Simha was that he was a very daring experimentalist because he would run these experiments with large amounts of explosives that were almost hand prepared, in the lab, and was never afraid of them. And also he was, as a student, what I remember is that he would ask questions that were really out of box. For example, I remember in one of the conversations with George Irwin that we were having, I think Professor Irwin had developed the dynamic stress field equations for a running crack at constant velocity. And of course, the quick question that Simha had to ask him was that why can't we look at an accelerating crack or a decelerating crack? Why does the velocity have to be constant? Of course, that increases the complexities of the theoretical formulation by an order of magnitude. I do remember at one time we were doing an experiment on the roof of our building. These were large boulders. I think we were filling them with explosives. With Simha, myself, there was another undergraduate student, Ravi Chona, and a technician, Joe Wasky. And we would blow up these boulders. And after a few hours of doing these experiments, the department head came running up to the roof and said, "What the hell are you guys doing here?" Because there is plaster falling in classrooms. So that was the first time I realized the importance of spallation, that you run your experiments with explosives there, and then the plaster starts falling in the rooms. We also had a lot of other common interests outside the lab. Simha and myself, both of us liked playing cricket. And we were, of course, in those days, these embassies in Washington, D.C. had cricket teams, and we played for the Indian embassy in several matches. Of course, cricket was something that we loved, but more than that, we loved the food that was prepared there. Because as graduate student, that is something that really attracts you. So we used to go there and spend the whole day and play cricket matches. We also played some baseball on campus with students and faculty members. And Simha and myself, I think we were the only two players on the field without wearing a glove. You know, we were so used to cricket ball and playing that without gloves that we never felt a need for using gloves. So Simha, again, you know, I have a lot of these fond memories. I know last time I was there in Bangalore, not too long back, a few months back in December and January, you know, we shared a lot of these stories and had a good laugh over them. So, so let me get back to my technical talk here. And today I'm going to talk about some work that we have been doing for the past maybe 10 years or so on instability problems for these underwater structures. And over the years, you know, I think I have realized this is for the younger audience there, that if you want to be successful in attracting funding and keeping your research going at a good pace, you have to change the focus of your work with the same background and the same knowledge base that one has, but the focus has to change. So in my case, I have changed it about 6 times. So this is the 6th one. I don't know whether I'll change it anymore. I'll retire after this, but this is nowadays for the last almost 8-10 years, we have been focused on studying underwater structures that are subjected to complex loading conditions. Now, underwater type of activity here in Rhode Island is the smallest state in the country. It's about, and as you can see on the slide, 48 miles long and about 35 miles wide, but has 400 miles of shoreline. And we are surrounded by industries and organizations that deal with underwater structures. Some of you might have heard of the General Dynamics has a huge setup here. We make submarines about 20 miles from our campus. We have the largest naval undersea warfare center here in Rhode Island in Newport, not too far from our campus also. And the only naval war college, the internationally known college, is right here, very close to our campus also. There are almost 600 small companies that cater to these large organizations, and they all deal with underwater manufacturing and activities like that. This underwater work is also called as a blue economy. It's really huge. In USA, the sales for this blue economy are of the order of $600 billion, not million, $billion. And it is growing at an amazing pace. I think I was listening to one of the talks by here in Rhode Island that they were saying that this blue economy will become one of the largest contributors to the national economy of USA very soon. So our interests are in looking at these structures that are subjected to dynamic loads underwater in complex situations. So the motivation for this, I say I already gave you some of the motivation in my just in the last 2-3 minutes, but there have been some accidents that have motivated us to look at this problem of implosion of cylindrical structures underwater. This example shown here is of a USS Treasure. This is a submarine that was manufactured right very close to us here in New England. And in 1963, imploded at a depth of about 700 meters. There was a leak that developed in the submarine and imploded, and we lost several lives in that accident. This accident that is shown at the bottom here, this is an observatory underwater in Japan. Consists of these glass tubes, photomultiplier tubes. And in this accident, one of the tubes imploded, collapsed, and then in sympathy of that, 7,000 other tubes collapsed. So this was a big accident, loss of time as well as loss of money. There's a lot of activity these days in underwater structures. This robot that you see on the right-hand side, this was considered to be invincible. Was owned by Woods Hole facility here very close to us in New England. This collapsed at about 30,000 feet underwater in the Mariana Trench. And so there is this fear that you make these underwater structures and they could implode underwater and could result in a lot of loss of human lives, or could be in financial resources also. So recently there is a big, huge increase in the activities for these underwater unmanned vehicles. And this vehicle on top that you see here, this is the recent contract that Lockheed Martin and Boeing have received to build these extra large unmanned underwater vehicles with composite materials. But the interest is in deploying these unmanned vehicles underwater, both for use of, in terms of forward deployment, where they could be used after some years, or they could be used right away. But we believe that in the next 10, 15 years, the activity in water, underwater, will be similar to what you have in air in terms of aircrafts flying all over the place. So these unmanned vehicles will be in thousands and thousands of numbers in oceans. So dramatic increase in these kinds of vessels. And that requires us to look at the performance of these vehicles from a mechanical engineering, mechanics point of view. So the outline of my talk, I'll just talk briefly about this collapse problem, the implosion problem, and the experimental techniques that we are using, and then give you some examples of this implosion. And I also want to show you some other examples of work that we are doing recently, all dealing with underwater activities. And I'll try to be simple and brief. A lot of this work is published in literature, so if you want to know the details, certainly you can look at them. And I do want to mention one thing, that for the younger generation also, there is a lot of scope in this underwater type activities. So if you want to focus your research in that area, I don't think you will go wrong. So this implosion phenomenon here, what you see in this movie, you'll see this tube here. This is a composite material tube, is a carbon composite tube. And we are immersing this in water at a certain depth, it implodes, collapses. And you'll see this implosion process here. So this tube collapses in mode 3. You'll see 3 lobes and 3 valleys in here, and goes through catastrophic damage and deformation. And in this process here, what happens is that it releases a pressure pulse that could be detrimental to neighboring structures or tubular structures or plate structures next to it. I also want to tell you that it looks very dramatic here, but later on, after the experiment was over, the tube rebounded back to its almost original shape. So it was looking at that final shape of the tube, one would not feel or imagine this catastrophic nature of this collapse process. So during that collapse process, if you look at the pressure, so here is our tube I designate that by the symbol A, and we are looking at a pressure profile at a very nearby location, as shown by this red dot here. That's our pressure sensor. And we plot this pressure on the vertical axis as a function of time on the horizontal axis. So when the tube begins to collapse, then these walls are moving towards each other, and the pressure at this location will drop. And that pressure drop is shown by this under pressure region right here. So this pressure drop will happen till these two surfaces come in contact. So at this point, when they come in contact, it emanates a small acoustic wave that is seen here. And then this contact point spreads along the length of the tube, and we call that buckle propagation. And after that collapse is completed, during this process, initial process of this linear contact here, this rushing water that is surrounding this collapsing cylinder will come to an abrupt stop. And that stoppage of that momentum creates a pressure pulse that is very large. It's shown by this spike here. So this pressure pulse could be as high as 5 to 6 times the collapse pressure of the cylinder itself. And this is what could be very harmful to anything that is in close vicinity of this. For example, here you see these 3 tubular structures, and these could be pipelines underwater, could be other defense equipment or anything like that. And in this experiment, these 3 pipes that you see here, or tubes that you see here, are of such dimensions that the collapse pressure of this tube, the first tube, is lower than the collapse pressures of these two tubes. So when we lower this in water at about 1,000 feet underwater, this first tube collapses, and you'll see a shock wave emanating from it. And this bar that you see on the right-hand side will kind of bend, and this shock wave is going to initiate the implosion of this tube, and this in turn will initiate the implosion of this tube. And this is what we call cascading implosion or sympathetic implosion. There are very, very few studies in this area. I think this is probably the first one of its type on a metallic cylinders, and we have done some more on composites. In glass, people have seen this phenomenon before. So let me run this movie for you. So here you'll see. So this is collapsing now. You see this tube begins to bend here. And then because of that, this tube collapses, the shock wave, and then this tube is going to collapse, the third tube. So now this movie, this experiment was done, and it's a very high-speed phenomenon. So the cameras we were using, if I don't remember exactly, but they were used at 100,000 frames per second or more. So we have slowed it down for you to observe this, but it's a very dynamic and phenomenon. By the time you blink your eyes, the whole thing is over. So the technique that we use for looking at these structures is the digital image correlation technique. And I think all of you probably know about this technique. Essentially, we put speckle pattern on the specimens, and then we observe the movement of those speckle pattern in a stereo format. So there are two cameras that they look at it, and we get 3D deformation, particle velocities and strains and things like that from it. Our experiments are conducted in a pressure vessel that is shown here. This setup that we have is somewhat unique. I have not seen something like this anywhere else in all my visits all over the world. So the uniqueness comes not because of the pressure vessel. This vessel we can pressurize to about 1,000 PSI. We fill this with water, and we have a compressed air on top here, and we use that to pressurize it. But the uniqueness comes in because of the optics that we use with it to probe the imploding structures. We use high-speed cameras. There are ports on this spherical pressure vessel. There are 8 ports, and we use high-speed cameras in those ports to observe this phenomenon. And the optics that we are using, this digital image correlation technique, I think we were the first ones to look at this digital image correlation technique for underwater dynamic applications. About 5 years back or so, we published a paper in the Proceedings of the Royal Society with our findings, and the technique is very robust and works very nicely for us. It is a little bit more difficult to use for underwater applications because of the water that changes the optical path of the light beam there. So this is a little bit more difficult, but I think once you get used to it and everything is calibrated properly, it works very well. In the tank itself, we have many pressure sensors. These are dynamic pressure sensors that are used to get pressures during the implosion process. The other setup that we use, the large tank that I just showed you before this, we consider that to be infinite amount of energy as compared to the small energy that is used in imploding the cylinder. So for us, that is like an ocean environment. But there are many applications where we want limited amount of energy to cause the implosion process. So this tube that you see here is filled with water, and our specimen or the cylinder that we are trying to implode is kept in here. So because this has a limited volume here, the energy that is used to driving this specimen that we have is limited in nature, and depending on the size of this implodable, this energy may be sufficient to drive that implosion or may not be sufficient to drive that implosion. This is how the tank looks from inside. So this is our imploding cylinder. We have got pressure sensors that are located all over the place, but sometimes we implode these cylinders by using hydrostatic pressure, and other times we will use explosives in the tank, or some combination of explosive and hydrostatic pressure to implode these cylinders. So we can look at these structural collapse problems under highly dynamic conditions of this external loading also. So what we did was, when we started this work, I think we spent a lot of time, maybe almost 8 months, 10 months, trying to develop this DIC technique for underwater applications. After we felt that we were successful with it, we did some simple experiments that we called calibration experiments to see if the technique was working well. So we had a specimen here on a stage that we could move to and fro, or this way in both the directions. And then this was filled with water. And we recorded our DIC images using these two stereo cameras. And then we had the exact solution because we knew exactly how much we were moving the stage. And from the DIC, we could get the displacements also. And then the comparison of the two gave us confidence in the use of this method that we had developed. So here what we are plotting is, on the vertical axis, we are plotting the measured displacements from the DIC technique. And the horizontal axis, we plot the true displacements, that is the stage displacements. And you'll see this plot line here, solid line is the true line, and these red dots are the measured dots. So both for in-plane displacement as well as out-of-plane displacement, our performance was pretty good, and we got a lot of confidence in this method of measurement. The errors that we had from the DIC technique were of the order of 2-3%, for out-of-plane displacement, and about 4 or 5% for the in-plane displacements. Now we have to remember that the DIC technique has some inherent errors in it. If you take an image without doing anything to the specimen and look at the DIC pattern, you will find that it'll give you displacements of the order of some percentage. So there is some inherent error, but I think for us as experimentalists, and looking at this extremely difficult problem of an event that is happening under not only one, but maybe combinations of extreme environments, I think we were very happy with this. So I'll give you an example. Here's a tube here. This is an aluminum tube, 35 millimeters in diameter. So when we collapse this tube underwater, the displacement that we will see at the central point here will be, maximum displacement will be 17.5 millimeters, because the diameter is 35 millimeters. So the radial displacement here should be 17.5 millimeters. And also when this, the two surfaces, the front and the back surface, meet each other, at that time, the velocity of this should be 0. So we wanted to make sure that this is really happening with our DIC measurements. So here on this side, we are plotting displacement. These color contours, these are just displacement contours. And this image here that I'm pointing with my pointer now gives me a displacement of 17.5 millimeters exactly. And at this time, if I look at the velocity contours, this color velocity corresponds to 0 velocity. That means the two surfaces are in contact. So once this contact point happens, then this begins to spread in both the directions. And there is some other physics that is involved in here. But all that is discussed in this. I think this was the first paper published for looking at dynamic underwater phenomena using DIC techniques. But it worked very well, and we were quite happy. And since then, we have been using it just to look at many different problems. So our focus is mostly on composite materials these days, and composites have been used extensively, not extensively, but they have been used in the past, but nowadays they're becoming more and more common in these underwater applications. So in 1954, the submarine USS Half-Beak used these composites in fair water cowlings. These things surround the submarine sails. And then they were tested after 11 years, and they were found to be in good condition. So 11 years of exposure to the seawater didn't reduce the properties much. I think there was a decrease of about 8 to 9% in terms of their strength values. Currently, all the submarine bow domes, these are made from, this is the material of choice for these sonar domes, and they're all made from composite materials. They're very large in size, 34 feet across and about 43,000 pounds. There is this certainly, but I think in the UUVs, the unmanned underwater vehicles, that will be the future, I think, for the underwater applications. Composite materials is the choice material for these structures. Our focus is mostly on composite materials. We have done some work on metallics also, but mostly on composite materials. And so in this, very quickly, I'll show you some examples. Collapse in open ocean environment, then collapse in this enclosed container here, then collapse, and these are all of importance to the naval industry. Collapse happening in where one of these is exposed to the ocean and the rest of it is confined. Then two tubular structures collapsing, one of them collapsing next to the other. I showed you this in terms of the aluminum tubes before. And then my student presented this yesterday, Shamal Kishore, of the interaction of this imploding cylinder with a nearby structure, especially when there is water on both sides of this plate here. Yeah, so I'll just say a few words, very quick words on these. So for the open ocean environment, a lot of energy available. This one I'll focus more on looking at these cylinders that are sandwich structures or double hull structures. And I'll show you this. So we are looking at cylinders that are fabricated like this. We have an outer shell, there's an inner shell, and there is a filler material in here. So this filler material, if you bond this material to the two surfaces of these shells, then if it is bonded, then the terminology used to describe the cylinder is a sandwich structure. If there is no bonding between this and this, then we just call it a double hull structure. So when it is bonded, of course, it is going to resist shear deformations. When it's not bonded, it will not resist shear deformations. So if you look at the collapse of these cylinders, then, of course, if you plot the change in radius of these cylinders on the vertical axis as a function of the pressure, for elastic buckling problem, you should have a linear change in radius as a function of pressure. And at some stage, there'll be instability and it will collapse. But for these two cases where you have filler material in here and this bonded, unbonded, the collapse actually is controlled more by perturbations that happen on the surface of these cylinders. And they dictate when the collapse will happen. So those perturbations are suppressed when this is bonded and as compared to when it is not bonded. So if I'm plotting change in radius here for a double hull structure and a sandwich structure, for a sandwich structure, the collapse happens at a much higher pressure as compared to a double hull structure that shows more perturbations. Now we are able to measure these perturbations in our experiments, and I'll show you in the slide here. So these are as the structure is submerged in water deeper and deeper, you start seeing these localized areas of deformation. So these are the incipient modal deformation points, and this is where the buckling starts. So we are able to make measurements of this for those structures, and then this is what dictates buckling in those problems. So if you look at the buckling pressure or increase in buckling pressure as a function of the different types of filler materials, these are different density forms, 5 different density forms that we used, and there's 4 different density forms that we used in here. The double hull structures where the foam is not bonded is down here, and when you bond it, the buckling pressure certainly increases. Now there's a lot of work in here. I'm just showing you in 1 or 2 minutes. As you can see here, we published this in Journal of Mechanics and Physics of Solids paper and in experimental mechanics papers last year. So you can get a lot more details in this work. So one of the things that we observed was that when the 2 cylinders collapse, if the axis of this collapse is minor axis, you see that here, if they are collinear, then this whole collapse happens in one shot. There is no, so the whole cylinder, will collapse. Both of them will collapse in one shot. Whereas if these two are not aligned, then there is some dwell time. So the top cylinder collapses, the second one collapses a little bit momentarily later than the top one. Now this dwell time is extremely important in some naval applications. And certainly if one can control this dwell time, then that makes a big, I guess it's important for Navy to know that. So some of our emphasis was on looking at these dwell times. So this is the collapse phenomena that you see here. Of course, this was with dwell, this was without dwell, and this thing happens so fast that you may not be able to see that, but this is how the two tubes collapse. Both of them are collapsing. There was a small dwell in that, and this one collapsed in one shot. Those papers, of course, have more details, so if anybody is interested, you can. So one thing I wanted to point out here was that in this collapse, this is the specimen shown here. We are making measurements of pressure close to this collapsing structure. And we plot this pressure on the vertical axis here as a function of time. I only want you to see this black curve here. So you see that again, as in a buckling problem, the pressure drops when the cylinder collapses. Sorry about that. And then this is the composite materials. You see all of this cracking and things like that in composite material. So the outer cylinder collapses, and we see this pulse coming out after the collapse is on top of the second cylinder, inside cylinder. And then there's a small dwell time, and the inside cylinder also collapses. And then you see another peak coming out. So there are two implosion phenomenon here, and both of them have their own pressure signatures in this problem. So I think I'm going to go and show you the second example of this implosion of this composite in a limited energy environment. And here we are doing these experiments in another tube. So this is the tube that has all the water in it, and inside there is a specimen that we are looking at. So what I want to point out here is for experimental mechanics people, the quality of data that we get even under such complex conditions, because here you see the cameras in the spherical tank. We were able to position these cameras perpendicular to the windows. Here, the window is it's not perpendicular to this light path, and that does cause some issues, but we were still able to get some very nice data. So this, depending on the diameter of this inside specimen that we have, the specimen may start the instability process, but may not be able to collapse completely because if this is larger in size, the amount of energy in this whole space here will be smaller. So I want to show you the quality of experiments. So this is the tube, the green thing that you see here. And at this point, we're making measurements of displacement and pressure both. So there are two pressures that we measure at this location and another location, but I'll show you at this point the displacement and pressure, and you'll see the radial displacement is plotted in blue color and the pressure in the red color. And so look at the blue color here. This is the displacement, and this is the pressure profile. And all this data, very nice data comes out from these experiments. And this case, particular case, the cylinder undergoes vibrations, but doesn't collapse. Now, there are, without going into too much of details of it, there are many, there's a lot of interest in this vibration problem for underwater community, because when the structures vibrate underwater, they do leave a signature, and that could expose them to anyway, so this it's more from the experimental mechanics point of view. I think we can capture some really nice data from experiments like this. Now we're plotting the displacement here. You could also plot other quantities of interest, like particle velocities or strains or something like that. So in the case of smaller diameter tubes here, inside here, so this smaller diameter tube, this will collapse completely. And this is very interesting. And this collapse here of this tube, I'm looking at pressures at different points, channel 1, 2, 3, 4, like that. And I just want to focus in this presentation on this channel 1, which is, I've plotted this pressure on the vertical axis as a function of time on the horizontal axis in this blue color. So and this is the end of that tube that we are pressurizing to collapse the cylinder here. So as the collapse process starts, you see this pressure drops at this point, and at this point here it begins to cavitate. So this is all cavitation that is happening here. Some sort of bubble is forming. But before this cavitation starts, there is some small amount of time where the liquid is in tension. And this part, liquid is in tension, is kind of not very common to for people because liquids are in compression, not in tension mostly. But it reminded me of a story when I was a graduate student and I was taking a class with Professor George Irwin on fracture mechanics. And at that time, Professor Orawan from MIT was visiting, and Professor Orawan is no more, but he was a giant in the field of plasticity. So he told us that during his doctoral dissertation, not the dissertation, but his comprehensive exam, the committee asked him a question as to how will you measure tensile strength of a liquid. And in those days, this was in 1920s, 30s, I think the extreme value problems were in fashion. People were studying them. And I think it was in the 30s, this energy balance, the Griffith's energy balance had come out at that time. So he answered that question by assuming a bubble in the column of liquid and did the energy balance between the surface energy and the strain energy in that liquid and predicted the tensile strength of that liquid. So there is interest. Then very recently when I saw this phenomenon, I went on the web and looked for papers on tensile strength of liquids. And I was amazed. There were many, many papers where people study liquids in tension. Anyway, that's an anecdote on the side. But in this experiment also, we were able to capture some really complex data using our experimental techniques. I just want to say a couple of words about implosion in composite tubes, where one end is exposed to ocean. So our ocean is this big spherical tank. So we put this other tube that we have inside this big sphere, the spherical tank, and this is our implodable here inside here. We implode this and then photograph this and measure pressure on this container that is on the side at these different locations. And in this 2 slides that I will show you, I will focus on pressure at the bottom of this and on the top point here, which is open to the big spherical tank here, this point here. So those 2 points. Okay, so when the tubes are of smaller diameter here, they they collapse, and then in the pressure at this point, there are different pressures plotted here. But if we look at this pressure that is plotted in blue color, so pressure is a function of time, and this blue color you see, we again see cavitation and small tension here at this point, and then this oscillates in harmonic fashion and decays and damps out. And that's what happens to other locations also, but this is the only point that cavitates. And this point here, this is green in color. See, this green color shows some oscillations like that. Okay. Now, if I change the radius of this cylinder and go to larger diameter tubes, then this tube, when the instability starts, it doesn't collapse right away. So it will start vibrating a little bit, and then a little bit later in time, this energy that is outside here, this tube is in the big tank, so the energy outside drives this implosion process further. And now if I look at the pressure pulses here at this end, here at the bottom and at the top and here, we find there's no cavitation observed till very late when the tube collapses. In this blue color, you see this starts showing cavitation. But we also start seeing cavitation at this point. This green line that you see is the pressure at that point, and you see this becoming 0 at this point here, or equal to the, So this point also starts showing cavitation. Now, this is something unique. When the student showed me these results, I didn't believe him and asked him to repeat the experiment. And he did that experiment again and got the same results. And I asked him to put 3 sensors here, not 1 pressure sensor, but 3 sensors. And all of them showed cavitation. Now, I don't know exactly how to explain that, but this may be a problem for fluid mechanics people to help us with these CFD type simulations. But we do see cavitation both at the bottom as well as the top of this container. So now I just want to show you very quickly the example of 2 cylinders next to each other in composite material. So here we did experiments in this big tank again with 2 composite cylinders. One of them is slightly longer than the other. And because of the change in the length, the collapse pressures of the 2 is slightly different. So we put these in the tank, and then we pressurize it so that the first one collapses, and then we were looking at the response of the second cylinder. Okay. So here, this is what we think is happening. These are the 2 cylinders. This longer one collapses. We call this primary tube. So as this collapses, this pressure next to it drops. So this second tube is the surface is kind of sucked into it. And once the collapse process is complete of this first tube, it emanates this pressure pulse. So it starts moving this surface outwards in this direction. And then there are two possibilities that this second cylinder could also collapse completely or could go into this vibration mode. And these vibrations happen both in bending as well as breathing modes. So this paper we are almost done writing, and I tell you this is a very interesting problem, and using DIC to distinguish between these bending and breathing modes itself is a challenge. But the student, again, Shamal Kishore, who's probably on this, attending this conference also, did this work, and very soon we should be sending this out for publication. So here is this one here, this collapse of the second tube is dictated by several different things, but in this case, at least we are changing the spacing between these tubes. So in this case, the spacing is half the diameter. In this case, it's 0.32. And you'll see here, when I run this movie, this tube will collapse on top. This will go into vibration mode of bending and breathing, but doesn't collapse. Now change this dimension a little bit, and you see that the first tube collapses, and the second tube also collapses here. So this is an interesting phenomenon. Again, a lot of interest in this work for the oil industry as well as the Navy industry. So now this is just the distance is one thing, but I think we observed very carefully, and we have made some careful measurements that what also dictates the collapse of the second tube is how the first tube collapses, the orientation of the first tube. Because depending if the first tube collapses in this fashion, then the pressure profile that is generated will be very different as compared to if it collapses in this fashion here. Both are mode 1 collapse, but the orientation is different. So depending on how they collapse, this second tube will see a very different pressure field. So in the paper that we are preparing, this is all discussed in there. So next I'm going to just say a few words about this, the fluid structure interaction of dynamic pressure pulses with submerged plates. So again, if you have a explosion, and of course we have, in this one, I'm not showing explosion, but you have, say, an imploding cylinder next to a structure, then how will that structure react to this? And this is, I think this was presented by my student in depth yesterday, but I'll just say just a few words here. So this is our setup inside this big spherical tank. So we have a plate that is shown here, this long plate, and then we have an imploding cylinder here. This is the one that implodes. And then inside this tank, we have pressure sensors located at different locations. And there is water, both this is all completely submerged in water. There's water in front of the plate and water in the back of the plate. So a lot of work in the past has been done, for in-air type of dynamic loads on these plates, or for underwater where this back of the plate was exposed to air. On one side, we had water. But in recent applications for the underwater community, there is a concern that if some dynamic phenomenon happens here, can this energy transfer on the back side of this plate? And if it does transfer, then what will be the amplitudes and that? And what is it really that really controls the pressure profile in the back here? So that was our intent. And this paper was published in JMPS, I think 2 or 3 months back. So a lot of details are in there. But here is a movie. This is the plate, and the implodable cylinder is on the other side of this plate. Okay, so you'll see that, and it is horizontal, laid horizontally. So when I run this movie, you'll see the cylinder is imploding on the other side, and these are all the displacement contours that develop on this plate. So this is, of course, of interest, but of more interest is the pressure profile that happens on this side of this plate here. And in order to understand that, we went through some modeling part. We started with Taylor's description of this fluid structure interaction and developed different. I won't talk about these, but these models incorporate plate bending, incorporate afterflow fluid in the analysis. I think my student presented this yesterday, and the details are, but the predictions from the model are pretty good. So we're looking at here the transmitted pressure profiles, so behind the plate. So this is pressure on the vertical axis, time on the horizontal axis here for thin plates and thick plates. And the experimental data is in red. The dotted line gives us the modeling part, and they match very well. So this is again, again we have this paper in JMPS 2-3 months back. So just want to say a few words in some recent work that we have done where we have looked at soft materials, and our interest in soft materials in these foam type of materials. And then we have done some work for naval submarine medical research labs that I probably won't be able to show you that data here in this talk, but so we are looking at organs, things like lungs and intestines and all subjected to.
Professor Shukla,
Yeah.
sorry to interrupt, but we have 5 minutes.
Sure.
We'll take some questions after that. Thanks.
Okay. So this soft material work, I just want to show you very quickly for underwater applications. So here is a PVC foam material that is underwater. And again, we are using DIC to observe this thing. And our interest is in getting the constitutive behavior of this material. So pressure on the vertical axis, and we are plotting volume on the horizontal axis. So you see, this is a movie of this foam material underwater. This is hydrostatic collapse under quasi-static loading. And again, here, the working with the DIC for underwater application was a little challenging with our cameras and the water and the cylindrical vessel here. So, but we got some good results. So you see pressure as a function of strain for several different types of foams. So you can get the hydraulic crush points and densification regions for this very nicely. And then if I do the same thing under dynamic conditions, but for dynamic conditions, we needed to design and build a tubular facility. This is called what we call the underwater shock tube setup here. We introduced the shock or dynamic loading by using an impact striker bar at this end here. We have a window here. The specimen is kept right in there, and we measure the DIC displacement data on that specimen and the pressure with these pressure sensors. So when we don't have any specimen, the pressure will decay like this. But in this region here, where we have the specimen and we measure pressure at these two locations, these are pretty constant. So we are using, again, high-speed photography to visualize this, high-speed cameras to look at the specimen. And this is the movie for high-speed application, shock coming from the left side and loading the specimen. And then again, we can look at the pressure as a function of time plot or volumetric strain as a function of time plot to the red curve here. And we see that there is a decay. So when there is a delay, this is the pressure pulse. It comes at this time, and then this is the deformation. So there is a delay in the deformation process, certainly because of the inertia effects. And again, these are all detailed in these two papers that I showed you here. So the dynamic paper is this, and Impact Engineering Journal came out last year, and this is the quasi-static work here. So this, we have interest in, as I was telling you, for the medical facility, we are doing work on some. So what, I can't show that, but I can show you this experiment here. This is the effect of blast loading on human skull. This is a 3D printed human skull, similar properties as human skull here. We have an explosive here. This is all underwater at a certain pressure. And we are doing DIC on the surface of this and making measurements of pressure. So our hypothesis here, or at least the thought here, was that when the explosive pulse comes and hits the pressure, and if you are using pressure measurements outside the skull in kind of determining how much injury is inside, or that may not be right. One has to make measurements of pressure right inside the skull. Now, in our experiments, are very simplistic. We have no material inside the skull. It is hollow, but we have a pressure sensor that we inserted from here. So there's one hole here that we insert the pressure sensor inside the skull, and we make measurements of pressure outside and inside, and we fire. So when I fire this explosive, you'll see that the explosive will hit the pulse, and there'll be a bubble that will form and hit the skull. Also, there'll be a lot of cavitation that you see here. So there's an explosion, and then the water oozes out from the lower part here, and the two eyeballs come out, and the water comes out. Now, this movie has been slowed down a lot, but this water coming out from the eyeballs is at a very high velocity and from here. So there are a lot of interesting problems that one can study here. This was just a demonstration experiment. We have done some work that is, so this, the pressure measurements that we have, pressure as a function of time, pressure as a function of time, inside the skull and outside the skull. You look at the amplitudes here, 15, 17 megapascals. This is almost 33 megapascals here. So there's a big difference. So I think the measurements, but it's amazing that, there is no work available in literature on traumatic brain injuries for underwater divers. And there's a lot of work on traumatic brain injury for in-air shock loading centers and hundreds of people, but underwater there is nothing available. So here is the DIC data that we get, and I'm not going to show, but we can get some very nice deformation data on the skull here. And lastly, just want to say that we have established an institute here. It's a collaborative institute between our university and Connecticut in collaboration with General Dynamics. This National Institute for Undersea Vehicle Technology, you can see the website here, has many different focus areas. There are 12 different focus areas. One of the focus areas is also advanced materials and underwater shock. So our work is mostly in that area, but we have a pretty large activity with about 70 faculty members involved in this activity and several different companies. So there is a lot of work. If you want to see more details, you can go on this website here. And lastly, just want to acknowledge that a lot of all this work that I showed you was funded by Office of Naval Research from different grants. And of course, the graduate students are the key to all this work. They work very hard, and we of course present it and get the credit, but they are the real workers here and real, I think I've been very fortunate in my 40 years of career of having some very good graduate students. They think outside the box and come up with new ideas that are really are the ones that keep the research going forward. Thank you very much.
Thank you very much, Professor Shukla, for a very interesting talk. We have quite a bit of interest from the audience, so we'll have some time for a couple of questions. We'll start with Shailesh.
Hello, Arun. Thanks a lot for your.
Professor Sima, yeah, go ahead. Go ahead.
Are you able to hear me, Arun?
Yes.
Yeah, I can hear you.
Arun, are you hearing me now? Thanks a lot again for the lecture. Like good old times we had at the University of Maryland, long time ago, the last millennium. Thank you very much.
It was a pleasure, Sima.
Shailesh, okay, Shailesh says his microphone is not working. His question is on the screen. I'll just read it out. He wants to know if you need any type of special material for speckles in your underwater studies. And also, can you briefly talk about challenges in getting good quality images underwater?
Yeah. So I think, no, I don't think we need any special type of material for underwater studies. We do have to remember that sometimes if you're doing experiments that are going to be very long duration, then you have to worry about the speckles not detaching, So, one of the assumptions in DIC method is that there should be a direct contact of speckles with the specimen. So, but there is nothing special that was used here. I would suggest that that you read that paper that we wrote in Proceedings of the Royal Society, so that you know the calibration methodology for this work. Other than that, there is not a whole lot of difference actually in the DIC techniques. For dynamic work, you certainly need high-speed cameras and you need intense light sources because the amount of light that is available for the short duration of exposure times should be sufficient. But these underwater applications from DIC speckling point of view are, I think, simpler as compared to the work that we have done at high temperatures, where the speckling method is a little bit more cumbersome. But these are not bad, very simple.
Okay, I have a quick follow-up to that. The color image you showed with the skull, what exactly was the color map representing in that case?
It was the displacements of the skull, so you're getting out of plane displacements on that skull.
That's the two camera.
Yes, those are 3D DIC.
I see. Okay. Thank you. All right. Vignesh, you have a question? Please go ahead.
Yeah. Thank you, Professor Shukla, for a great talk. Very impressive experiments, I must say. I have a question about fluid structure interaction, especially after the collapse of your structures. And I understand that you mentioned 2 examples where you were talking about the breathing per se of a neighboring structure and the question of cavitation. I was wondering if there have been any thoughts on doing imaging of the fluid itself in front of the structure, maybe using a laser light sheet. I can imagine PIV will be very difficult because you have to seed the fluid, but then maybe imaging the cavitation itself, would that be an option, or was that something you ever considered?
No, yes, I think so. Of course, there is a lot of interest in imaging. Actually, I should have shown that image. That student who did the work on looking at the cavitation was able to photograph the cavitation bubble on the surface. Now, that imaging that we use for the cavitation to look at the cavitation bubbles forming, that just shows the bubble. So there's nothing more than that, So I think to get quantitative information, we need a better system, but and maybe a sheet of light might be something that we could try. But because we have very powerful cameras. Right. Our cameras can do about some of them can do 10 billion frames per second. So we certainly, in terms of time resolution, we have the capability of photographing those cavitation bubbles. And so I think if you give me just 1 minute, I want to show you something here. Let me see if I can go back. I think I don't have control of my screen, but anyway, in the pressure profiles that we had, we had the peak pressures. Okay. I won't go to that, but anyway, the peak pressures we were seeing on the pressure sensors, because the cavitation was happening on pressure sensors themselves. So when these cavitation bubbles collapse on pressure sensors, you get very large spikes, but 40, 50 megapascals. And first I thought they were some kind of an error or some kind of a discrepancy with the sensor itself, but those were bubbles collapsing on the sensors, and we were able to photograph them.
Aha, okay, thank you.
Thank you. We have time for one last quick question from Naveen. Naveen, do you want to go ahead?
Hello, sir. A nice presentation from your side. Actually, I'm very fascinated from your experimental setup. So my question is related to your high-speed camera orientation. So you have oriented outside the setup, and you have made an angle of 17 degrees. So I would like to know what challenges you faced for the orientation perspective and alignment with the specimen, so that you make a proper images of it.
So that's a very important question. I think, and for experimental mechanics people, that one has to be careful with that. So when you do your calibration process, the included angle between the cameras is very important, and the angle relative to the surface of the window is important also. So those included angles that I showed you in my images, that was kind of a threshold of the angles that we could use in our experiments. Beyond that, the calibration errors would increase quite a bit. So one has to be careful. Now, that's not coming from any kind of theoretical analysis. It is more from the calibration process that we have performed over the years. So that included angle of, I think the lower it is, the lower, the better it is. So certainly you can't make them too low because of the physical size of your cameras. And in case of the spherical tank that we have, the windows are perpendicular to those two cameras. So it's not that big of an issue, but certainly with flat surface windows, then it becomes a bigger issue. But if I was making that measurement, my suggestion to you, or if you're going to make it, is to keep those angles small. And 17 degrees is probably the largest probably one can go.
Okay, thank you very much, sir.
Okay, thank you very much, Professor Shukla. I think there might be a couple of more questions in the Q&A box. So if you get a chance, maybe you can address them at your convenience.
Sure, yeah. Thank you very much.
Thank you for joining us for the symposium as well.